And now we reach the end of the road. It's time to cover the final section of these videos, the monetary policy section. And we're going to call this coin Bitcoin. How about that? Pretty cool, huh? Just thought of it. So yeah, we're going to call this one Bitcoin, and it's going to be a short and sweet video, especially compared to that ungodly monster POW coin. And that's because Bitcoin's monetary policy is short and sweet. It's very simple, and that's one of the best things about Bitcoin is how simple the monetary policy is. And so as it stands, our POW coin we inherit from last time suffers from inflation. And that's because we made a bit of a deal with the devil. We said, in order to fund our clever mechanism for securing our network without any trust, or with minimal trust in a third party, we're going to rely on inflation to incent mining, as we called it, which is securing the network, mining participation. And so yeah, it's kind of a deal with the devil. And as you know, inflation is wealth confiscation, and we should strive to eliminate that. And so we would like to create a monetary policy, meaning like basically an algorithm for how many coins exist at any given time. We want that algorithm to eventually taper off and have no inflation. And so that we can call this like the global inflation problem. When you look at the long time horizons, like the complete life of our coin, it currently suffers from inflation. And that's because we issue the same number of coins in the Coinbase transaction every single block, and it's hard-coded in our code as the block underscore subsidy. That's what the variable was called. And so a better way to do it would be to have a fixed terminal, like a terminal supply. It's just once we reach a certain point, a certain block height, no new coins are created. That would just be much better, because then we would stop confiscating wealth from our users, or from our the holders of this coin. And so there's a separate problem, the local inflation problem. These are the things I call them to kind of distinguish between the two. And because we're going to want to solve these separately with very different methods. And so the local inflation problem is if a ton of miners come online, the supply will grow very quickly. If you read the Bitcoin Standard by Saifedean Ammous, he talked about this quite a lot. He gives this great example about what would happen if you tried to monetize something like copper. If someone tried to turn copper into money, as they bought up the supply, the price would rise drastically, and soon it would be 10 times as much as it used to be. And then all of a sudden, all the gold and the silver miners, and basically anybody who mines any kind of metal, would stop mining what they were mining and start mining copper, because it's so much more profitable. All these old copper mines that had been abandoned would be turned back on again, because they are now profitable again. And what would happen is that you just have this explosion of new supply, and everyone would get diluted, and that's inflation. And so the same thing would happen here. This is something that happens with any commodity money that can be produced. As interest rises, more people try to produce it, and normally you get more supply then, right? Which is more inflation. And so we want to use the unique properties of software to basically sort of revert this every time it happens. And so let's tackle the global inflation problem first. So here's an idea. What if we have the block subsidy every n blocks until it hits zero, right? And it will hit zero, because this is like a logarithmic decay, and logarithms decay pretty quickly. So in order to make this work, we must add a separate miner incentive that can gradually replace the block subsidy. So we want two subsidies, or we want two incentives. One of them is the block subsidy, and this is like 100% of the reason why anybody would participate in mining at the beginning. And then over time, we want a separate subsidy that can basically slowly replace it. So, over time it'll start to be, a little bit more, maybe it'll start 1%, and then this second subsidy will get to like 10%, and then it'll be 50, and eventually it'll get to be 100 as the block subsidy, which is inflation, as that goes to 0. And so we'd call these fees. The difference between the sum of the transaction outputs and inputs will go to the miner. So we have some of this clever input and output structure that we defined all the way back in Bank Divisacoin, which probably feels like forever ago. We can use these clever data structures we have to just like tweak a few little parameters and say like any outputs left over from the signed inputs will just that will be kind of the miners, and the miner can just add those to their Coinbase transactions. So the Coinbase is the block subsidy plus any signed transaction inputs that do not create outputs. Like whatever's left over in the creation of outputs from the signed inputs will also go into will be added to the block subsidy in the Coinbase transactions amount. And so let's go and implement that. So now we're back in the terminal, and we're in the root digital cash directory. And if you ls, all of a sudden we got so many files here. And so we saw last time we were working completely from the POW coin directory. So now we're going to be working from the Bitcoin directory. And so if you ls the Bitcoin directory, you'll see a couple of files. So we have like, this one will probably be gone by the time you see it, but I've been just sort of tweaking things here. But we'll have a docker compose.yaml, a Docker file, a requirements.txt. I'll actually probably kill this one too. This is also redundant. We could be using just the root requirements.txt. This is just telling each Docker container what Python packages they need to install, and so I think it's exactly the same as that one, so I should probably delete that as well. But and actually the tests, I'm not going to actually use any of these tests, so this will look completely different when you see the video. Oh well. But we're going to go in the same direction where like the POW coin or Bitcoin _1, Bitcoin _2, Bitcoin _3, and this one will be the last one. This one will actually also be gone, so it'll be Bitcoin 1, Bitcoin 2, and then Bitcoin.py. And so these we'll kind of go through these incrementally. So if you get stuck, just remember to diff between like the file we're working on and these solution files, as I kind of showed last time. So what we're going to want to do is we're going to want to create a mybitcoin.py file in the Bitcoin directory. And the file we're going to copy is the POW coin file. So we can say cp POW coin.py, and then bitcoin/mybitcoin.py. And so now I'm just going to cd into that, and you don't have to do this obviously if you're using like a IDE or something for the text editing, but I'm going to cd in here, and then I'm going to open it in Vim. Okay, so now I've opened my bitcoin.py file, and let's go and look at the mine forever function. And so what we're talking about here is we're talking about making the block subsidy, basically the amount of the Coinbase transaction, to be variable, right? We're going to vary it. It's going to start high, and it's going to get lower and lower and lower. And so this is where we actually set this in normal operation. We do it. We also set it in mine Genesis block, and we'll come back to this just because we kind of treat this one separately. And so here at prepare Coinbase is where we're going to want to basically pass in a value for the Coinbase subsidy for the amount of the Coinbase transaction. And so this is what I'd propose, something like this. Just we'll pass in a variable, and on this previous line we could say like we could just ask the node, hey node, get us the block subsidy. Basically calculate the current block height and do a little math to figure out how many times we've done, how many halvenings we've gone through, and based on that tell us what the current subsidy should be. And so this block height will just have to do that. It'll just have to do a little bit of math to see, based on the block height, how many times have we cut the subsidy in half? And so, given the initial subsidy, you can figure that out. And so, yeah, that's basically in this section of the video. This is the one thing we're going to implement. And so before we do that, let's update prepare Coinbase to give it a second parameter called block subsidy. So if you hop up here, we'll see prepare Coinbase. We'll stick it here because this is like an optional parameter that I don't even think we use it anymore. I think I added this for like basically backwards compatibility reasons, and so I forget. But coin block subsidy will be a variable, and so instead of having it call a global block subsidy, we're just going to have it do the one that's passed in. So block subsidy, and so yeah, so now we can pass in a variable amount for our Coinbase transactions, and it'll go in there. And so next, let's go and create this get block subsidy function. Move it to the middle of the screen here, and so let's just stick it on that. So I'm at the bottom of the node class. Remember, connect block was like one of the last things we did in the reorgs video. So yeah, this is like the reorg code up here, and so we'll say def get block. And so it doesn't need any parameters because all it's going to do is just read this basically how many blocks are in our chain and do a little math on that. And so we're gonna call a couple of global variables that haven't been defined yet. And so after we write this function, we'll go and define those. So first we're gonna count how many halvenings we should have had by now. And I'm going to say, so we're going to say how many blocks are in our chain, and then we're gonna do, I forget what the name of this operator is, but this is like division where you just grab the like how many times it divides. So like if we go over to our terminal, we could say like 10 by 3, right? And so this will just say how many times it divided. And so if you recall, this will just tell you the remainder. Right, so like this one is basically like, this is this, and then this divided by this is this, right? That's kind of the relationship between those. So yeah, we just want the whole part. Basically, see like how many times have we kind of has our chain like completely filled up another halvenings worth of blocks. And so for this next line, I'm just going to type out the formula, and then we'll hop over to the terminal, the Python shell, and I'll sort of give you an example of how this works. So it's going to be return 50 times. I'm going to tab complete that, but of course I haven't defined it yet. Satoshis per coin we will divide the initial block subsidy 50 times the number of Satoshis per coin, 5 billion by 2 halvenings number times, right? This is basically the same as divided by 2, divided by 2, divided by 2 over and over again. So we just 2 to the raise 2 to that power is how many times we're going to divide it. So if I hop over the terminal here, I'm going to say Python, and for me that opens up Python 3. And so I'll say I'm just gonna give you an example of what this will look like if we over like the first, let's say 35 halvenings. So for I in range, let's say for halvenings, print 50 times these underscores and numbers just are basically dummy variables. They just allow you to visually see the orders of magnitude. So you can spot this is 100 million and not a billion or 10 million. So yeah, so this is what it would look like the first 35 times we do it. And so you'll see it starts at 5 billion, then goes down to 2.5 billion, then to 1.25 billion, and then it goes to 625 million, right? So it's just getting cut in half every time. And so it gets lower and lower and lower, and finally it gets down to 9, then to 4, remember, because we're just taking like the whole part of the division, we're throwing away the remainder. Then it goes to 2, 1, 0. So after about 33 halvenings, we hit 0. And so this naturally we could just like run this halvening every day for a month, and that would be our network would basically reach the terminal state, and we could test out to see what kind of a fee market evolves right at the end here. Probably not going to happen in this silly class, but or this silly thing, but whatever. And so that's what this this formula will look like. And so yeah, that's hopefully that makes sense. So that's just what we're coding our block subsidy to basically decrease like that. But we're not going to decrease. We're only going to do this maneuver once every halvening interval many blocks, right? Right. So for the first, let's say halvening interval is 100, right? So for the first 99 blocks, this will return this, until this gets up to 100, this will return 0, and then it will return 1, right? And you'll have to go another 100 blocks, and then it'll return 2. Another 100 blocks, and it'll return 3. So it would, if you printed it out, you'd see this one 100 times, then this one 100 times, and this one 100 times, right? So it's not like this is kind of an abbreviated version of it, or like a sped up version of it. So the next thing we have to do is to redefine some constants. So if we go to the mining code, remember we had these like constants sort of sitting here in the middle of the file. So I want you to delete these, or cut them and bring them up to the top of the file. And so I'll stick them here. So what we're gonna do is we're gonna move this one here. You can just kind of put these wherever you want. Let's see. So I think these ones are sort of like logically the same as those ones. So the first thing we're gonna do is we're gonna delete this block subsidy because we don't need it anymore. We're making that like a dynamic function that the node class can calculate on demand, and so we can delete that. Now we're done with that, and next we have to define the halvening interval in satoshis per coin that we just talked about. So for halvening interval, it's equal to, let's say, 60 times 24. And the reasoning for that is that this would be daily, assuming 1 minute blocks. So like this is in seconds. So 1 minute blocks, we'd have 60 seconds times 60 would be 60 minutes. So that's an hour times 24 would be 1 day. So the interval would be basically 1 day's worth of seconds. Or 1 day's worth of blocks, excuse me. So this would be if you this would be one day's worth of blocks. So yeah, that's important. The unit is blocks here, and so the next variable is satoshis per coin, and this is just equal to 100 million. And so the idea here is there's nothing special about the number 100 million. We're just copying Bitcoin. But the important thing is that this basically allows us to make our coin more divisible. Remember way back in Bank Divisicoin, we were talking about how we could make this really divisible if we just added enough units. Well, now we just did. There's just going to be trillions and trillions of units of our coin in satoshis. And so now we can make, our smallest unit's going to be so small, we're not going to touch it unless the coin takes over the whole world, like we all expect Bitcoin to, right? So now that we have those two defined, there are two tiny little things we need to do. Remember when we said earlier that mine Genesis block also is something that calls prepare Coinbase. So remember up here we said when we call prepare Coinbase, we gotta also put in block subsidy. So here we'll want to stick in block subsidy. So actually, let's just say since we got probably enough room here, we can just say we can just call node.getBlockSubsidy inline, and we could probably do this up here, but I think this looks a little better that way. I think, yeah, this works. So that's one of the two places we have. Well, now that we changed prepare Coinbase, we had to update it everywhere it was called, and so we're done with that. And so the other side of Coinbase transactions is validation, right? So we have to look at validate Coinbase, right? So validate Coinbase is called whenever we're attempting to validate a block that's going on our main chain. So this would be when this validate transaction flag is true. And so this is when if you recall from the last video, this is when we're actually adding to the main chain. It's kind of not the best variable name, but it'll do. And so what we used to do is we used to check that the Coinbase transactions amount was the block subsidy, right? But we just killed the block subsidy. Now the block subsidy is no longer a fixed variable. It's sort of an on-demand thing we can calculate. So we'll just say self.get block subsidy, right? Instead of the hard-coded value, we're going to look it up on demand. And so with that, we're basically done with this section of the video. And so we don't have any unit tests to convince you that it's working, but in order to do that, and we're going to go and revert these changes basically as soon as we make them. But I want you to copy this variable halvening interval. I want you to comment out the old version of it, which we'll be reverting to. And actually, yeah, this is how when I want to test things, I always copy it and leave the good version there, just so I don't forget that I did this. But let's just say the halvening interval is one block, right? Remember, the unit here is blocks, and so I could probably make that a little clearer. I could say like halvening interval in blocks, but I'm just going to leave it. So let's make it one block, and then let's say in def mine forever. Here, when we say mine a block, let's make it an f string, and say with transaction with subsidy, and then what we want here is mined block dot txns of 0, right? So grab the first one, the Coinbase, and then grab the first tx out and grab the amount of that, right? So again, horrible ugly code here on this line. This is real ugly, and we need to make sure the f string is properly formatted. So that looks right. And so again, we're going to revert this as soon as we do, as soon as we run it. But I just want to show you what happens here. So if we go and open up the Docker file, we want it to say mybitcoin.py. Just always want to make sure. And so if we run over here to our terminal, clear that. And then we say, remember, we're in the Bitcoin subdirectory, so you want to make sure you're in there. And then you want to just say docker compose up -- build. And so we don't have to say dash. Remember the last time we were doing that -f thing, right? We were doing it like this. We don't have to do that anymore because we only have one docker compose file. If you look in the directory, it's just this one. And so it's like it just uses that one by default. So remember, this is the same one where like node 2 and node 1 don't know about each other, remember? So peers node 2 doesn't know about node 1. This was that's what the docker compose file looks like. And so let's say docker compose up -- build. And if I didn't screw up anywhere, this is going to be kind of interesting. We're going to play out like the whole monetary policy of our coin in about 30 seconds or a minute. So you see it starts with, it mines a Genesis block and it doesn't say anything. So the Genesis block was at 5 billion per coin. And so here we see at height 1, right? So 1 after the Genesis block, this is 2.5 billion. And so then it goes to 1.25 billion, then down to 625 million. And so it's just getting cut in half every single time. And so this is all before the second node even gets online. So by the second node, you know, we're already down to like the hundreds of thousands, it looks like. That's about 1 million. And so a little further, the third node comes online, and now we're down to 19,000, right? We're getting pretty low. Mine to block with subsidy 74, that's insane. Down to 18, 4, 0. Mine to block with subsidy 0. Height 34 and height 3 is the same. So yeah, this hopefully this convinces you that we are actually we have implemented halvenings. We have implemented a partial solution to the global inflation problem, right? Let's have the block subsidy every n blocks until it reaches 0. We did that. One small problem. We actually need to, we don't have this, once we get there, now like no one would ever mine this because there's no reason to mine, right? There needs to be some sort of other reward we can give them for mining. And so that's where fees come in. So if you, let's just kill this. So if you ls, this is where we're at right now, Bitcoin underscore 1.pi. And so now we'll start working towards Bitcoin underscore 2.pi. And so this is how it's going to work. Let's go to mine forever. Actually, let's go and undo these things we just did. So that here we are back to where we were, right? We go back to here and let's go to mine forever. And so in mine forever, you see how we get the block subsidy and then we pass it into prepare Coinbase. What we'd really want to do is pass in like block subsidy plus fees, right? Here's the first incentive for people to mine, and here's the second one. As we drop block subsidy towards 0, this will hopefully, in a free market, will start to compensate for it. And so we need a function that can calculate these fees. And so let's say we have fees equal node.calculate fees. And we'd have to pass in a group of transactions that it could calculate the fees on, or you know, alternatively we could build the block ahead of time. So we build the block down here and we could pass that in. But I think it's a little easier to just calculate the fees first on the basically the transactions that will go into our block, which is node.mempool. So let's just pass that in here. And say that's what the argument is to calculate fees is just a list of transactions, and that's what the mempool is. And so let's go and write calculate fees. So we'll once again go to the end of the node class here that's becoming monolithic and ungodly, and I wish it wasn't so big, but let's write one more method for it. So def calculate. Right, we said it was going to take as an argument just a list of transactions, and then we'll say fees equals 0. We'll just initialize the variable fees, set it to 0, and then we're going to go and iterate over every transaction, and we're going to count up the inputs and the outputs, and then we're going to increment fees at the end of this for loop by the difference between the inputs and the outputs. So I'm just going to start typing this out, and you can follow along. So for transactions, we're going to say inputs. You can do this double assignment. So I'm just setting inputs and outputs both to 0 because every time in the loop we want to start from scratch, and then we'll say for every transaction input in the transaction, we're going to increment the value of inputs by the amount of the corresponding UTXO. So txin has this out point. Out point is the key in self.utxo set, and that will return us a tx out, which has amount defined on it. And so we can do the same thing with tx outs. For transaction out in transaction.transactionouts, let's add up the outputs. And this one's a little easier because the output is on the TX out itself. Right, so we just look it up. Right, because TX in doesn't have an amount on it. You have to actually look up the corresponding UTXO, or the corresponding TX out. But here we already have it, so that's a little easier. And then we'll say at the end of the for loop, once we've gone through each, at the end of each iteration, we'll say we'll take the we'll say inputs minus outputs. So inputs will always be bigger than outputs, right? Because this is like everything you sign and can reassign, and outputs is basically like everything that you do assign and give to someone else, to some other address, right? And so what's left over is the fee. What's left over from the inputs that you sign and contribute to the transactions, and the outputs that you sort of create, that will be the fee. And so we'll say fees plus equal inputs minus outputs, right? So every time we go through, we'll add this up. And by the end, once we get through this for transaction in transactions, we can just say return fees. And I don't have any comments in here, but I think this is really actually pretty clean code and pretty self-explanatory. So by the end, we'll be able to just say, for every transaction, whatever Satoshis were left over, we're going to basically add those up and return them. And so now if we go back to our mine forever, that makes sense. We're going to pass in a list of transactions. It's going to give us our fees. And then for Coinbase, prepare Coinbase, we're not going to just use the block subsidy. We're going to also take the fees. So we'll give ourselves just a little bit more in case there are fees. And so to give you a little bit better understanding of how this works in practice, let's look for prepare simple transaction. Right? Prepare simple transaction is here. And so in prepare simple transaction, we will want to add one more variable to the function called fee. And so how fee will work is basically we will, the important part is here where we assign the change, right? So we'll have one output where we send the money to our counterparty. And then here is we send whatever's left over to ourselves. So instead of change, instead of change, but just being the sum of the sum of the inputs minus the amount we're sending. Basically, this would be the sum of the outputs, right? Because we're only doing one output. The sum of the outputs that aren't the change. Sorry, it's a little confusing. But so here, instead of saying just the inputs minus the amount, we'll have inputs minus amount plus fees, or plus fee. Right, and we'll put parentheses because we want to kind of treat these as this, as one. We want to, it'll subtract the amount and also then subtract the fee off of it. And so here we're strictly making the change that we give ourselves smaller, and the miner will then collect that fee for themselves. Does that make sense? We're strictly like when we're sending coins, instead of giving ourselves back transaction in sum, TX in sum minus amount, we're going to give ourselves back transaction in sum minus amount minus fee. So we're just giving more money to the miner to bribe them to secure the network and take our transaction, right? Because eventually there would be there would be limited space in the mempool. We don't have any block limits here in this little demo, but if we productionize this, we'd probably want to add some block limits. And so a couple other places we'd want to add this fee term is here. Basically, every time where we had amount previously, we want to change that into amount plus fee. And so now handle simple or prepare a simple transaction looks good. And so let's look for where we call that. So it should be way down here somewhere. So prepare simple transaction is here, right? So here, this is when we're doing the Python Bitcoin.py TX Alice Bob 10 when Alice sends Bob 10 coins. Let's say the fee here will be 100 Satoshis. We'll just hard code it for now. You can play with this and do this. What you could actually do is you could add another variable here, like fee. And as long as you did everything right here, and you probably have to cast it to an integer because it's strings by default, I think. You could have a thing where you like here you do like, you know, -- fee. You could have it, you pass it into the command line. So that'd be kind of a cool thing you could do. Exercise the reader, exercise the student here. But let's jump back here. So yeah, so when we call prepare simple transaction, we'll pass in a fee of 100. And so there's basically one other place we care about calculate fees, and this is again the validation. So let's look for validate Coinbase. And so you see here, remember we were asserting that this is equal to block subsidy. Well, now that we just added the fee to block subsidy when we prepare Coinbases, right? So now when we validate them, we'll also want to check that this is not just equal to block subsidy, but it's equal to block subsidy plus fees. And we'll calculate fees right here above it. So fees equals self.calculate fees of, and here's the tricky thing, we're going to want to, since we need to pass in all of the transactions that are in the corresponding block, what we'll actually want to do is pass in block.transactions of 1 to the end. So skip the first one because that's the Coinbase and get the rest of them, right? And so you'll notice transaction is not, or block is not defined here. So we'll want to change how you call this function and ask that you give it a block. And that makes sense because every kind of block has one Coinbase. And so here, instead of having, we had TX, so when we pass in block, we'll just say TX equals block.txends of 0. We'll just kind of redefine what we already had so our existing code works. And then we just need to go and look for everywhere we call validate Coinbase, and instead of passing in the Coinbase transaction itself, we'll pass in the block, and then here in the function we can pull it out. So here we'll see it. We have validate Coinbase, and so we'll just delete that and just pass the block in itself. And so before attempting to run this, there's one tiny little subtle thing we need. So here in it should be, yeah. So here in validate transactions, some code we haven't touched in a very long time, we have these input sums and output sums. Because we're now basically giving this option to leave a little bit of money out and allow the miner to collect that, we can't assert that the input and the output sum is always the same, because now it's actually possible. One thing you could do now is you could sign a transaction. You can make a transaction with one input that's signed and 0 outputs. You could actually do that now, and that would just be interpreted as 100% fee, right? And if you look back in Bitcoin's history, people actually screwed up and did this. They sent like 200 Bitcoins to the miner, right? And the miner just got to collect it, and happy days for that miner. So instead of input in sum equals out sum, we want input in sum is greater than or equal to out sum, because this might decrease, output sum might decrease in certain circumstances when we give some fees to miners. So this now has to be greater than or equal to. And so if everything's good, and I pray to God it is, we can hop back over the terminal and we can run our Docker Compose, and we can source a virtual environment in a separate window. Remember, Alice is Satoshi here, so we can actually have her send some coins. Alice will send Bob, let's say, 10,000 coins. And so if everything's good, it we can go and look at Alice's balance now. We can go look at Bob's balance. I should have looked at Alice's to begin with, but I think she probably had one Coinbase worth of transactions. So balance Bob. And so Bob now has the 10,000 coins, right? So that's good. So let's look at Alice. Well, that's interesting. So it looks like she originally had 5 billion coins, right? She mined the first Coinbase, so that would make sense. And so it looks like she's missing 10,100, right? So she sent 10,000, but then she also is missing 100, and that makes sense too, because if we look down here, remember, we set fee is equal to 100. So on top of the 10,000 she gave Bob, she passed in another 100, and that was eaten by the miners. So if we go and look at the balance of all the miners, oh, look at that. So node 0, right? He's got all these coins from mining, but he also has a coin he also has this like spare 100 sitting on the end, right? Node 1 and node 2, you know, we're back to doing the difficulty adjust, or the halvenings very infrequently. So these are, you know, the only way this node 0 could have gotten this 100 coins is as the fee that this node got for mining Alice's transaction to Bob. So that's pretty interesting. Like our fee, we can now specify fees. Miners now have 2 ways to make money, and our protocol is no longer so like the deal with the devil that we made to sort of bootstrap our network using the basically the free money of inflation. We now have like an exit method there. We can opt out slowly over time by cutting our Coinbase subsidies in half, our block subsidies in half. And so that's pretty cool. Like if we go back to our PowerPoint here, we now having the block subsidy every n blocks. It will reach 0 in 33 blocks or so, plus or minus 1. We added a fee incentive, and we actually implemented all this. So that's great. The other problem is the local inflation problem. Remember the problem that arises if you have a huge change in the interest in mining this currency, which would happen, guaranteed to happen if this network took off and if anybody had an interest in it. So I'm just going to kind of walk you through this because they're not really analogs in normal commodity money like gold. So it's kind of it takes a second to wrap your head around it. And so it takes, as we learned in the POW coin, it takes 2 to the difficulty bits guesses on average to mine a block. If the rate of guesses increases by a factor of n, so guesses are happening n times faster, meaning there are n times more guesses in a unit time than there were previously, then the block time, the time it takes to mine a block on average, decreases by a factor of 1 over n. So they're inversely related. If you increase the rate of guessing, then block time goes down, and that makes sense, right? Like, you know, if you know, anytime you're doing some sort of a guess, right? And this is true for like any kind of work, you know, if you're like digging a hole, right, and there's just one of you digging, and then a couple of your friends come over and help you dig, the rate of hole digging is going to decrease by a factor of 1 over n because you're all going to basically contribute the same amount of work. So this is just like any kind of work. So that should be pretty straightforward. And then so here's the key insight. So if block time decreases by a factor of 1 over n, then inflation per unit time increases n times. And that's because n times as many blocks are produced per unit time, right? So in the whole example, you're just going to get n times as many holes. Here we get n times as many coins, and that's a problem because it sort of like breaks the contract that users have with the coin, where they expect that their slice of the pie is predictable. So this is kind of like, you know, this could, if you have a bunch of supply created, if a bunch of inflation happens, then the user, the holder is just probably going to dump it because it's like, this is not what I signed up for. This is bad money, right? Inflation is like the enemy of money. It's the thing that kills you. And the solution here is difficulty adjustment. So I'm going to kind of introduce some terms here that we'll be using in the code, and I'll have a picture after this, a really beautiful picture that you guys are really going to like to illustrate this in a little more detail. So first, we have this idea of a difficulty period, right? It's just a grouping of n blocks, and you start with the genesis block. So the first n blocks, that's the first difficulty period. Then you have the next n blocks, and the idea is the mining difficulty would be the same throughout these n blocks, and in the first block, basically when you cross one of these difficulty periods, the first block in the next period you'd reevaluate how difficult the problem should be to compensate for how quickly or slowly that group was actually, it took to mine that group of blocks. So that's what we're going to call it. We're going to call it a difficulty period. And so let's define like a target block time as so m seconds. So we have two variables now, n and m. And so then we'd say the target duration of a difficulty period, right? Sort of like the duration we're aiming for in a given difficulty period that we want to hit every time is going to be just n times n, right? It's going to be the number of blocks times the time it takes per block, right? So then the units cancel out, and this is a time. This is n times n. It's just number of seconds. And so at the beginning of every new difficulty period, let's calculate the duration of the previous difficulty period, right? So when we get to the block at height n, so that means there would be n blocks before because you start at 0. So it'd be 0, 1, 2, 3, all the way up to n minus 1. Once we get to block n, we're going to want to say, well, how long did it take to mine those previous n blocks? And then we can compare it to n times m. And if the measured duration of the difficulty period was above the target, right? The target n times m, then we need to so that means that the mining problem was too hard, right? Because the network basically took longer than we wanted it to, right? So the network took too long, meaning the problem was too hard, and so the solution is to make the problem a little bit easier. And we can do that by decrementing the bits of the next block. So if bits were 20, then we move it to 19. If bits were 256, which hopefully it never gets that high, but I don't think it's possible, but you move that down to 255. And then so that would just mean the problem gets half as hard. So we're not as granular in our I think Bitcoin's quite a bit more granular, trying to make like exactly kind of hit the nail on the head with making precise difficulty adjustments. We're just going to go by factors of 2, and we're going to adjust a little bit more frequently than Bitcoin does, but it's the same idea and it's a lot simpler to implement. So less confusing math equations. So what happens if we're below the target? Well, we just do the opposite. If we're below the target, that means blocks are being mined too fast. And if blocks are being mined too fast, that means the problem is too easy. And the solution is to make the mining problem harder. And we do that by incrementing the bits, right? So we just add 1 to what the bits were in the previous difficulty period for every block in the next difficulty period. And here's the promised diagram of how this stuff works. You'll notice that I got sick of Google PowerPoint app, whatever you call it, Google Slides. It's quite hard to draw diagrams, and they're the POW Coin Part 3 reorg animation diagram almost killed me. So I want to try something new. I busted out the iPad, charged up the Apple Pencil. Hadn't seen the light of day in about 6 months, both of them. And so I drew this up for you. So I'm trying to just give you more of like a visual reference for what's going on here, because the code in this chapter is like kind of, it's like a bunch of like really minute little like math operations, like arithmetic, but it's like, it's kind of confusing for me at least. So I want to have like a visual reference to look back on in the video and to sort of give you an idea what we're doing ahead of time. And so The idea is we have these chunks of blocks separated by these dotted lines, and each chunk of blocks is one of these difficulty periods, right? So this is the first difficulty period. This is the second, third, fourth. And so we would call this like difficulty period 0, difficulty period 1, 2. I mean, this is one of the things where it's like indexing from 0 like throws everything, all the, it's like, what do you call it first? But it's like index 0. So you always have to deal with that. But so these are the different difficulty periods. And so you can see on each block, it has the number of bits of difficulty actually on the block here. And so that's a big difference from what we've had previously, right? Previously, the bits of difficulty is a global variable that's shared across every block. Here, the bits of difficulty changes, but it never changes within a difficulty period. See, once we change it for a difficulty period, it stays there. And then once we cross over, we do a check, and the check will say whether we should raise it or lower it. And so for example, here, our check said we should raise it. And so you see by this little blue arrow up arrow, we went from 16 bits or 15 bits to 16 bits. And then we stayed at 16 until the second difficulty period ended. And then we said, okay, now let's go back down to 15. And so we did that. And so and then we continued and we went down again. And so that's the idea. I haven't, and so for y, we would choose to go up or down. That's kind of this area down here. So what we would do is we would measure the duration each difficulty period lasted. And we would compare that to the target. Remember the target difficulty period, n times m. We would compare that to our target. Basically, how long we want it to take for n blocks to be mined, right? And if the measured duration that it actually took to mine those blocks is less than the target, then we're going to increment the bits. We're going to make the problem a little harder, just like we said over here, right? That's the second one. If we're below the target, so that's what we said here. If we're below, then we increment bits. We make it go up. So that's the second case here. The first case would be the next block. So here we say, okay, well, let's imagine that duration was greater than target. So it took longer to mine these blocks than we wanted it to. Well, then we're going to lower duration, or we're going to lower bits, and we're going to make the problem a little bit easier. And then let's say, we do it again, and we go down to 14, and this would just continue on forever. And so this is our difficulty adjustment scheme. And now the one unanswered question that remains is, how do we measure duration? And so duration is, think of it this way. We want to know when we stop mining blocks in a difficulty period and when we begin mining blocks at a difficulty period. And so if you can just imagine for a second that every block has a timestamp, it just says like block.timestamp will say, we'll have a time on there that indicates when that block was mined. So, this is something that hasn't existed previously, but we'll be adding this video. So if you add a timestamp to each block, then if we're imagining this difficulty period here, the time that we started mining it would not be this block's timestamp, right? Because this block's timestamp is when we got one block. We'd already been mining one block's worth by the time this timestamp comes in. The timestamp that would indicate when we start mining on this difficulty period would actually be this one here, right? Because as soon as this block is mined, then we are mining this block. We're hashing and trying to get it. So that would indicate when we begin this second difficulty period. But when do we end? Well, that would be this one here. As soon as we have this block mined, then we are done on this difficulty period and we're on to this one here. And so, since timestamps, we're going to be using Unix time, and Unix time is just the number of seconds since the beginning of 1970. It's kind of an arbitrary way of measuring time, but it's very convenient because you can do math on it because it's just a float. It's just like a decimal, a number with decimal places. And so to measure how long this difficulty period took, we would just have to subtract this time. We would say this timestamp minus this timestamp, and that would say how long it took. So it would be this timestamp minus this timestamp. And for this third difficulty period, it would be the same thing. We would take this timestamp and subtract from it this timestamp. And whatever left over is how long it took to do the third difficulty period, and so on. And so you'll notice that there's one, we have to make a special exception. Think of this first difficulty period, right? You notice how every time we're peeking back to the last block on the previous difficulty period, we actually don't know when the Genesis block, when mining began for the Genesis block, because the Genesis block is kind of different, right? It's presented whole and complete. It's like the Genesis block is like, it just popped in mind. It's like Jesus Christ, right? It's like it just shows up into the world complete and perfect, but you don't know how it got that way, right? So the Genesis block is like Jesus Christ, and and so you don't know how long God spent mining this. Basically, God's is Satoshi, right? So you don't know how long someone spent mining this, and so we'll make a slight exception on the Genesis block to measure the first difficulty period. To measure the first difficulty period, we will just say this block minus this block. So it'll be a little different, right? Because we can't go, this block to some previous block because we don't know. There's nothing prior. So it'll result in a slightly different, like the duration of this first difficulty period will be a little off for this reason, and also for the reason that the Genesis block has to have a hard-coded timestamp. And so, there was probably some duration of time between this block actually getting mined and the network being deployed, right? There's all these like logistics of deploying a network. And so this first difficulty period will be kind of out of whack. But luckily that's, we assume our network's going to run a long time. And so that really doesn't matter if this is just, if the math here doesn't really, it's not really valid. That's just one, and everything after that will be valid. So again, this is just a little overview of what's going on here. I know you were all jealous at my artistic skills, and just get an iPad is what I got to say. If you want to, you can do this too. Just get that iPad and that Apple Pencil, and yeah. So yeah, let's move to the text editor and actually build this sucker. Okay, so now I've opened up my Bitcoin.py, as you can see here. Let me full screen this thing. Yeah, so I'm in my Bitcoin.py, and as you can see here, my Bitcoin.py, and yeah, so the big thing we're going to need to do in the very last portion of this this digital cash series of videos, what we're going to need to do is we're going to need, you recall how here we're talking about how many bits are on the block and the timestamp on the block. Let's inspect the block class. Nothing regarding bits or timestamps, right? Like these don't exist yet, right? And so let's do a little review where the bits are set now. So bits are set on a global variable. And so if we search for just DIFF capital in capitals, you'll see that these are the only two places. So we only define bits here just to have it as an easy, like, kind of separate variable to toggle the POW_target. And that is what we actually use. And so if you search for POW_target, you'll find that we use it here in validate block. It's the first thing we do when we see a block. We check whether that block has sufficient proof of work on it or not. Basically, does it start with enough leading zeros in the binary expansion of the binary representation of that number? And so then we have the opposite condition. So here we're checking less than, right? Because this is what it should be. This is a good proof of work. And so here we have the opposite. We have greater than or equal to instead of less than. And the reason for that is because this is a condition that it's not a good enough proof yet, right? So while we still have a bad proof, we're basically going to increment the nonce and try again, right? And so if we exit out here, if we exit out of the loop here, this means now we have a good proof, right? That means this was false. And so block.proof was less than POW_target. And so, so then this validation condition would be true because it's less than. And so yeah, if we search again, just hop around, those are the only two places that we use it. And so the idea here is that we're going to want to put bits on the block class, and then we're going to want to have a target property that kind of calculates this. It does this exact calculation based on the block's bits. So let's do that. Okay, so the first thing we need to do is we need to add a bits property to the block class. And so let's go to the block class and let's add a bits property. Right, same as always. And then let's hop back to where we were, and I want to get this, grab this POW underscore target and just delete that line. And I want you to go down here just below where we defined block.proof, and we're going to do the same thing. We're going to call it target. Right? This is basically the number. This is the number that we need to have satisfied. You know, so here I'll show you. So instead of comparing block.proof with POW underscore target, the global variable, every time we're going to compare block.proof with block.target, right? So block.target just takes the bits on this block and does the same math on them and says basically how many leading zeros you need. And so in this way, we can have every block have a different required difficulty. And our protocol itself will, in the validation code, will enforce what the correct number of bits are for any given block. And so now that we have these defined, let's look for every place we use POW underscore target. So here is the first place. So instead of comparing block.proof with POW underscore target, which no longer exists, we want to compare it with block.target. Right? That's pretty straightforward. And so let's hop to the next place. And so same thing here. We just want to replace POW underscore target with block.target. Okay, so now that we have all of the instances of POW underscore target replaced, we now need to look for every place we create a block instance. So I'm going to search capital B block with a parenthesis and see every place that we instantiate one of these suckers. And so here, the first place is in mine forever. This is no longer valid because it doesn't declare bits. So what we want here is we want to say something like this: bits equals node.get next bits. And let's just, for now, we'll figure out what we're going to pass in there. But we basically just want to ask, like, hey, node, how many bits should this block have, right? We want the, and so this is like the protocol itself, our node implementation, the sort of like enforcer from on our view of the protocol is going to say, hey, this is how many bits. It needs to be 17 or it needs to be 25. Right, and so that's how we're going to get bits when we declare a new block. And so here's the other place where we create a block in MineGenesis block. As you recall, the bits or the MineGenesis block is sort of just handled differently, and that's just to kind of simplify all the rest of our code because it's kind of a little different. And so what we want here is, and I'm going to say initial difficulty bits. And you can see we're spilling all over the place onto a new line here. And so I'm going to say right here, we're going to break to a new line. And so initial difficulty bits is not set. Remember, we had difficulty bits, but we don't have initial difficulty bits. So I want to go to the top of the file and see where we had initial difficulty bits. You know, like it's not used anywhere. So I'm just going to put initial in front of it. And so now we have initial difficulty bits defined here, and it's used here, right? And so now if we look for any other places where we define block, that's in a repr method. So here we have bits, there we have bits, and there's nowhere else. So now we're good. We've basically made our code legal again. We are now passing in the correct parameters. The only tricky thing is that this one actually doesn't exist, right? This function doesn't exist, and we don't know what we're going to feed it. And so before we decide actually exactly what the API for this function is, meaning like basically how we will use the function. And so like one important thing about a function's API is like its application programming interface, the programming interface. One important thing is like what arguments is it going to take? Should we give it a block here? Should we give it something else? And so in order to make that decision, I want to show you the one other place that we'd need to have this function called. And there's sort of like with every function, what we generally will call it like, we'll often call it like once in the preparation of a block, and then we'll call it another time in the validation of a block. So we'll be calling the same functions to both construct and to validate blocks. And so that's it makes sense because the same rules always apply. So what we're going to need to do is we're going to need to look for the validate block function. So def validate b. So here's validate block. And so what we're going to need to do here is we're going to need something approximately like this. So if you recall, this validate txns flag is basically when we are validating this block against the main chain. In this video, I'm gonna abuse this flag because it's sort of like, now it's a good name because we're doing all transaction related stuff, but I'll start doing like difficulty adjustment related stuff in here. And the reason why I do it in here and not outside is because we don't like strictly speaking need it, and it just sort of complicates things. Like if a block that's on a branch, like if this code doesn't run, that means that the block was being added to a branch. And so if it was added to a branch, if it ever gets reorged to the main chain, this code will run. So it's not like we're ever going to let anything in that we shouldn't. But it's just kind of easier to reason about if we only have to consider the main chain. So like we'll be able to just say like, self.blocks of index here, because we're just assuming we're dealing with the main chain. And so this is something I should probably refactor in like the second time I do these videos, but let's just keep it simple here. And I don't want to, like, the purpose of these videos again is not to do it perfect, but to do it in a way that you understand the core mechanics, right? Because this network is not meant to be deployed in production. It's meant to teach you how it works. And so what we're going to want here is we're going to want something like this, like check difficulty adjustment, right? And so that's the bits. We got to check that the bits are right. So we'll say assert and then here we'll say ... because we don't know what we want. And so one thing I'll have you notice is, so I'll split the screen and show the two sides. So like on this side, like what we'd really be wanting to do is we want to check the next bits of, like, we want to basically pass in here the, like, I'll just put it in quotes just to like make it clear that it's like hand wavy. We want to pass in the previous block here because we want to say, like, given the previous block, this block's bits are correct. Right? But over here, this is more like this block, right? And so you'll recall that there's like a block.prev ID, right? It's basically a pointer at the previous block. But in order to actually go and find this block, we'd have to go and like do a for loop over the whole blockchain, and it's kind of silly. And so I think it would be better if this block, yeah, so in order to find this previous block, we got to do like a for loop over everything, and it might be in so I think it would just be the cleanest solution to, instead of passing in a block, just to pass in a block ID, because it would work in both scenarios, whether we're using the current block or whether using the current block's parent. So that's what we're going to do. We're going to say block.prev ID. And yeah, so this is the way we make sure that the bits are set correctly. We're not going to ever accept a block into the main chain if the bits were set, if the bits weren't set according to the rules of our protocol. And so likewise, let's hop over here and say, what is it? We need node.blocks of -1.id. So node.blocks of -1 is like the tip, and then ID is that block's ID. Before we go and actually implement this getNextBlocks method, there's one more thing we need to do. So remember this, total work. This is where we check if if a branch has passed our main chain. And if this is true, we reorg. And so, if we look at this, our total work function is not finding the most work chain, it's finding the longest chain, right? And so this is one of the original bugs in Bitcoin. And this is something that Peter Woola discovered and fixed, and I believe. And so instead of just returning the length, what we're going to want to do here is we're going to want to do something like this. Sum of block, excuse me, let's do 2 to the block dot bits. And so what we want to do is we want to basically just guess, like, how many we need to calculate how many guesses did it take to mine this block, and then we're gonna sum that up for every block, right? And so total work is basically just like total number of guesses it took to build this chain. Cool. So now that we have that, let's look towards the end of the node class and start writing this getNextBlock method, or sorry, getNextBits. And so let's just stick it here at the end. So I'll pull it up a little bit. So def get. And so I'm just going to start typing out some comments just to sort of sketch out how the method will work. So first we got to find the block, right? Because we can't always pass it in because we don't always actually have the block. So let's just pass in something that we always have the block ID, and then we can just go find the block. It's a little inefficient because sometimes we're looking up a block twice, but who cares? And so next we're going to check, hey, are we crossing one of these dotted lines? Are we entering a new difficulty period? Because if we're not, we're just going to stick with the bits we had, right? There's nothing really we need to do after that if we aren't entering a new difficulty period. And then so that's, well, I'll put another comment in, only change bits if we're entering a new difficulty period. So basically, we'll return the function early here if we aren't if we're not entering a new difficulty period. Calculate how long this difficulty period lasted, and think for a second, how are we going to do this? We can't, right? We don't have timestamps. None of our blocks have timestamps. So this is where we can just put, like, to do. Define block.timestamp, right? We're going to need that in order to do this little chunk of the algorithm. And so now that we have all the information, we know whether our the duration of our period was greater than or equal to, or greater than or less than our target. We can go and make those comparisons and either increment or decrement bits. And then here, we're going to log some information. There's quite a lot here. We'll want to log what the period is. Are we in the first, the second, the 10th, the 100th period? What was the target? What is the how long was the period duration? And what did we do to the bits? Did we increment them, decrement them? What happened? And so that's roughly what the function will do. And so let's tackle this one first, block.timestamp. And so just as a as kind of a reminder of what a timestamp is, let's hop over to the terminal and just enter Python 3. I can just type, like when I enter Python, it gives me Python 3 on my system. So you might have to type in Py3 or Python 3 or something. And so what we want to do is import time. And this is a Unix timestamp, if you haven't seen it. So it's just, actually we could do this like, so this is the type of timestamp we're using. You could Google this and read up a little bit. It's Unix time. It is the number of seconds that have elapsed since the beginning of Thursday, January 1st, 1970. And so the reason why it was this date is because this was approximately when, well, if you want to understand this, go read this history section. You know, it's like when this was about the time they were creating the Unix operating system, and they needed a method of recording time for the operating system. So this is what we're going to use, mostly just because it's super simple and widespread. It's you can add them because they're just integers, or they're just, excuse me, they're floats. So kind of exit out of that. So Google it if you've never heard of these, and so this is what they look like. This is the number of seconds since the beginning of 1970, and so the way you can do is you can write a function like this. Let me just type out a little demo and give you an idea what we're going to do. Print T1, print hope I didn't make any mistakes there. It's neat. So you'll see we have T1 is equal to this, ends in 40. T2 is equal to this, ends in 41, at least the integer part. And then when we subtract them, you'll see they're almost exactly 1, right? Because I did a time.sleep in the middle. And so this is the reason I think this is a nice little demo, is because this is the kind of operation we'll be doing. When I was saying in here, you know, we're going to be subtracting and doing arithmetic on the timestamps, this is exactly what I'm talking about, right? Like, let's say this T2 would be like, you know, this block's timestamp, and if T1 was like this block's timestamp, then we could say if T2 minus T1 is equal to approximately 1, we could say that 1 second is about how long it took to mine this difficulty period's worth of blocks. And so yeah, let's with that, I mean, you can kind of play around with this if you're not familiar with these, but just wanted to make sure you had seen that, because we're going to be playing with them. We're going to be using these quite a bit. So I'm going to delete this note to self, and I'm going to look for the block class, and I'm going to do the same thing we did with bits. I'm just going to tack it onto the end. Right, so just like we always do, and just like we did last time, let's look for all the places that we instantiate blocks, and we'll need to update them to include a timestamp. So here, when we construct a block to be mined, we want to just use our subjective timestamp, just use our computer's clock. So right, we'll just say this is our time. We're just going to give them our subjective time. And then the next time here is, this is a funny thing. So we actually need we need like a fixed number here, right? We can't just say time.time, because the different nodes in our little demo all spin up at the same time. So we actually want like a hard-coded time here. And this will like slightly screw up difficulty adjustment, because it'll make sure that basically the first adjustment always increases, because this, if we hard code a value in, it will be like super far in the past. And so, oh well, let's just take this, we can just take this whole thing and copy that over. And it also doesn't matter that yours is going to be slightly different than mine, right? Because you're obviously going to be watching this video later than, it's going to be a later time when you watch this video than when I record it, because it's going to take me some time to edit and finish and everything. So, and so these will cover the 2 times we instantiate block. We don't do it anywhere else. So let's hop back to our get next bits method, and we'll actually start typing this out. So remember we said that we're just going to be assuming that whenever we do this, we're dealing with the main chain. This is just an assumption to simplify things. I don't think, I don't know, maybe there is a problem with doing this. Maybe it'll open a denial of service attack. And if it does, all the better. So when we deploy this network next week or the coming weeks, we will actually get to test this. You can try to break the network, and that'll be more fun than getting it perfect. So let's just assume that we're dealing with the main chain here. So we'll find the block, and we'll only look on the main chain. So we're going to need to get the height, and the way we're going to do that is we're going to do a list comprehension, grabbing the ID for every block in the main chain, and then we're going to check what the index of this block ID is in that list comprehension. So we grab every block and block ID and self.blocks, and then that's just a list. And so lists have this .index method where you can just check at what position is some object, and that object we're going to pass in as block ID. So this will give us the height, and the height's important because this is how we'll check, like, hey, are we entering a new difficulty period? And then we'll grab self.blocks of height. Will give us the block itself. And so next, we want to know, hey, are we entering a new difficulty period? And so this is the block basically of the this is the block ID of the kind of last block we know about. And so what we'll want to look for is whether we'll need to look at the next. What we really care about is what the next height is. And so let's make a new variable, next. Right, so this is next height is going to correspond to the same block as next bits, right? That will be the height of the block that gets this number of bits that we're calculating. And so next we're going to want to check what the period is, like what number period we're on. Like, are we on the 0th period, the 1st period, the 2nd period? And then we'll want to also check at what height are we within that period. And so let me just type those out. Okay, so I'm going to take do division on this next height and just grab the whole part, like throw off the remainder, just say like how many times does it divide. And so this will just basically check how many times have we gone through a full blocks per difficulty period worth of blocks. And so the next one is we want next block So the next one we're going to just grab the remainder for this same division. So we're just doing division here, and here we're like throwing away the remainder, and all we care about is how many times it was divided. The dividend or whatever the hell you call it, I always forget those words. And here's just the remainder. We're just going to say, hey, what's left over when we divide it? And so what we care about is basically whether this number is 0, right? Because this will mean that we're in the first block of a new difficulty period. So just as some visual reinforcement. So for here, first period, this would be the difficulty period, and the variable would be a 0. It would be a 0 because we haven't actually gone one full difficulty period's worth of blocks. So when you divide it and just take the whole part, that would be 0. So these would all be difficulty period 1, and these would be difficulty period 2. And so for this block, this would be this would be the n plus first block. So it would be height equals to n, right? Because it's 0 all the way up to n minus 1. And so this would be height n. And so this, like, the number of blocks per difficulty period is n. So when we divide this height of n by n and just take the remainder, do modular division, we will get a 0, right? And so this 0 will mean we're at the first position in this difficulty period, right? If we did it here, this would be what would it be? 2n plus 1, 2n minus 1, I guess. Yeah, because this would be n minus 1, and this would be another n after it. So this would be 2n minus 1. And so for this one, if we divided by n, it would be like I think it would be n minus 1. It would be 1 short of n. So this would be like the last block in the difficulty period. So it wouldn't be 0, right? Only this first one would have this next block period variable equal to 0. And so now that we say only change bits if we're entering a new difficulty period. So here we will say if next block height, remember this variable I was just sort of poorly explaining, if this is not equal to 0, right? Because you're saying it's going to be 0 on these first blocks, right? The ones that get the arrow that actually change the bits. On everything else, there'll be 1 up through like n minus 1. And so and by the way, I think I mentioned this is not defined yet. This blocks per difficulty period. Maybe I forgot to mention that, but we're going to define that soon. And so yeah, if this is not 0, we're just going to return block.bits, right? We're going to say, hey, we're just keep it what it was. Don't worry about it. And then so next we want to calculate how long this difficulty period lasted. And that's where we really make use of these block.timestamp things we just created. And so and we're going to run into complications here, just as a word of warning. So I'm going to create this variable 1 period ago index. These are bad variable names, but oh well. And so what we want is, So I'm going to create this variable 1 period ago index. And what I want is height minus blocks per difficulty period. And so this will just take basically the last block for like this will be the height of the last block, or like the block 1 difficulty period ago, right? So if we're in one of these situations where we actually are crossing over, so the block underscore ID that we pass in to the function would correspond to a block like this right at the end, right? And then this variable here, like, you know, next height, like the next height, this next stuff would correspond to this one here. And so when we get to, so here is just basically checking that we're at this first position. And then here, one period ago is going to be height minus blocks per difficulty period, basically n. And so here, so this would be height. Height would correspond to this one. Remember, next height corresponded to this one. Height was corresponding to this one. So height minus n, minus blocks per difficulty period, would put us to this one, right? So we're going to want, like I said in the kind of intro, we're going to be comparing the timestamps of these two blocks. And so let me type this out, and then I'll mention like a little bug that's a big bug that's right here. So and so we just go and grab the block at that index. And then we're going to want to do an assertion, assert and then we're going to want to calculate how long this period took. So we'll make a period so we'll just say, hey, block.timestamp minus 1 period ago dot timestamp. And so like in the case that we're actually doing a difficulty adjustment, we'll be subtracting like a block like this, the timestamp of a block like this minus the timestamp of this guy, right? Or if we're crossing over this threshold, we'd be subtracting the we'd be subtracting this timestamp from this timestamp. Right, because this is the current block that we're entertaining. This is 1 period ago. And so I'm going to leave out this little, there's a little bug here that we'll have to revisit, but let's just like get the main gist of the function out of the way, and then we'll go revisit that. I'm more saying this to remind myself. So so we'll say calculate next bit. So if period duration is less than or equal to, and now we're going to have another new variable, difficulty caps lock is just the worst. Difficulty period. You have this one too? God, it's hard. Difficulty period in secs. Secs is for seconds, by the way. So we'll say if difficulty period is less than or equal to the how long it should be, right? So this is our target difficulty period, right? So remember here we were saying we will compare the measured difficulty, or the measured duration with the target, right? And so the target is this. This is the target, right? And so we're going to do the comparison. So if it's less than the target, right? So that's this one. If it was below the target, then we need to make the mining problem harder. And so here we'll say make it harder, increase it by 1. And we're going to save it in a next bits variable, mostly just because we're going to want to log this before we return. So we don't want to just, we'll eventually return this value, but we want to log it first. And then otherwise, we can say next bits, right? So in the case that it took too long, or took longer than our target duration, then we're going to make the problem a little easier. And so after that, we're gonna want to log it. We're gonna log quite a bit of information. So I'm gonna show you how to log like a big multi-line. We probably should have been doing this more, but so we want we're gonna do one of these things where we put some parentheses out in the front, so it's sort of like says what sort of part of the system it's logging about. And so what you can do in Python is you can actually do these multi-line strings, and they'll just be sort of concatenated when they're evaluated. And you can actually do f strings in the same way. So what we can do is we can just do multi-lines and treat, and it'll work as if we all wrote it in one big long ugly line. And so we can say like period. And so this is the next block period is this one. So this is basically what block period we're entering, right? So for this one, you know, when we're crossing this, the block period would be 1. When we're crossing this, the block period would be 2. When we're crossing this, the block period would be 3. All right, because we start at 0. And so we'll want to log that. We'll want to log target equals to difficulty period in seconds. We'll want to say how long it took. So let's say duration equals period duration. And bits, we want to say what we did to the bits. And so let's say block.bits. Remember, block is the block that we are basing it off of. So it's kind of like, the next bits will be the bits in the block that follows. And so we'll just do a little like arrow signifying what change we made, and say next bits. And one other thing is we need, since this is all going to get concatenated, we want some spaces in between each one just to make it look a little better. And yeah, here I should probably say difficulty adjustment, because it's more like difficulty period doesn't really make sense there. So difficulty adjustment is what we're doing. And so, so after that, after we've done that, and we should put this here, after that we'll just return, we'll return next bits, right? Because the function is get next bits, we got next bits, we logged what happened, and let's return it. So now some sort of semi-philosophical discussions about time. So one of the tricky things right now is, let me ask you, under what circumstances could that be a negative number? And so there's one time where this could be a negative number, and that's if we are crossing this first difficulty boundary. And so in that case, height would correspond to the height of this block, right? Which would be like n minus 1. And so blocks per difficulty period would correspond to n. So we'd be saying n minus 1 minus n. And so that would be equal to, that would be negative 1, right? So that would be a negative number, and you know, if you recall, what indexing by a negative number just counts from the back of the list. And so that would be really bad. That's exactly what we wouldn't want. And so to fix that, let's just say max of that number and 0. So just guarantee that we're always non-negative. And so in the case of the genesis block, this would just go to 0, and that would be good. So the one period ago would be the genesis block. And so yeah, that works. It's kind of a hack. I'm a little embarrassed by that code, but it kills the one, you know, a little corner case that would kind of ruin our day. And so so the next thing we have to do is we have to actually we have to define some of these global variables. So let's go to the top of the file, and let's go and knock these out. So let's for now, where should we put these? We should probably put these, so I'm just gonna rearrange these the way I have them in my solution file. It doesn't really matter. So yeah, and so actually block subsidy I think is gone. We don't need that anymore. And must have forgotten to, sometimes I get my solutions and this stuff gets a little out of whack when I re-record things. And so after initial difficulty blocks, we'll want to do, like the two that we wanted were blocks per difficulty period, right? And so let's just say 5, just for the ease of demo. Like we'll have 5 blocks in each difficulty period, just so we can sort of see it easily. And so the next thing we want is difficulty period in seconds. And so what we want here is we just want to say something like block time in seconds times blocks per difficulty period, right? We'll just say like, hey, how long should a block last times how many blocks in a period? And that will give us how long should the period last. And so in order to do this, we'll need to define this block time in secs, block time in seconds. And so this will, let's just say this is equal to, for now, let's just say 1, just so it'll kind of mine fast. And let's set this a little higher, like 18 or maybe 17. And so I'm just kind of doing some guessing since I've done this, you know, repeatedly. And so, so yeah, let's see here. So we are very nearly ready to run this. There's just one more problem. Let's see, how do I... Remember I made a comment about we need to check, we need to know that our block, we need to do a little bit of validation on timestamps. Like we don't want somebody to give us a timestamp that's like 10 years from now or something. Because at the moment they could actually do that and it would really throw off difficulty adjustment, right? They could say, hey, you know, this last you know, block took 10 years, make it easier, you know, or this last period took 10 years, make it easier, right? If you had the times float way out into the future. So in order to prevent that, we want to kind of do a little bit of validation on checking that the block timestamps are reasonable. And we can't do any like real exact checking, because this is a distributed network and different people's clocks are different. So our clocks are never going to be completely synchronized. So we can't say, like, given a timestamp, we can't say if it's right or wrong. What we're going to do is we're going to say whether it's reasonable or not reasonable. So in the same spot here, when we're entering stuff onto the main chain, we're going to do like 2 more assertions. And so let me just type these out and I'll explain as I go. So first we're going to check that block timestamps cannot be too far into the future. And so it wraps around, and then I'm putting this new line, I'm continuing the statement on the next line here. It's kind of ugly, but block too far in the future. And so the way this works is we're going to take the timestamp and subtract from it now, right? And so if this is a positive number, this will mean that this block's timestamp is in the future, right? Because time goes up as a number of timestamps. As time passes, the number gets bigger. And so if we subtract now from a number, that means that that number is bigger than now. And so that number is in the future. And so we're going to check if not only, like, if it is in the future, we're just going to like upper bound it by 1 difficulty period worth of time. So we're never going to, like the amount of time we expect a difficulty period to last is going to be like the most we will allow a timestamp to be into the future. And this is like sort of arbitrary, but we just want to have some like rough bound on like how far out in the future we're willing to accept a block. And usually this should never be more than like a couple seconds, right? And so the next assertion we want to do is we want to say that the block timestamp should advance every block period. So we're going to go and look at the timestamp of the block 1 block period ago, and we're going to compare that timestamp with this current timestamp, and we're going to make sure this current timestamp is bigger, because like within 1 difficulty period's worth of blocks, we expect the timestamps to increase. So we'll allow timestamps to actually go backwards in time for like, let's say 2 or 3 blocks, but once we get up to 5 blocks, our current N, our current blocks per difficulty period, we're going to say, hey, you got to start going, forward in time. And so we're going to do another one of these max things where we check that, we make sure we don't get a negative number. And this is a little implicit. This is kind of a crappy line here. I'm basically assuming that when we're doing validate block, we're extending the tip. So it would probably be a little bit better to say, like, to actually go and grab the height of this block. But I'm sort of assuming that when we do this, when validate block gets this far, that we are attempting to append to the main chain. And so so yeah, this is like kind of implicit, but I think it's good enough. And so we're going to say, hey, we want this current block timestamp to be bigger than the timestamp 1 difficulty period ago. Pretty straightforward. And so we'll want to do the little comment here. So if we run into this error, we'll get a nice message. block periods cannot go backwards in time. And okay, there my highlighter, syntax highlighter fixes itself. And so before we run this, I think there was one little, it looks like I made one little error here. So you see where I say assert block.bits is equal to that. Like this is illegal. This is using, we need a double equal. We want comparison, not assignment. Okay, so everything looks good. So let's hop over to our terminal, kill this, clear it, and say, and actually, before we do that, let's open our Docker file. And yep, so this has been me testing. So make that mybitcoin.py. And let's hop back here and try running it. Okay, so we have one miner entering, and the bits are 17, so it's a little higher than usual, so the mining is going to be a little slow to begin with. And so that's what I aim for, is like a slow mining to begin with, and hopefully the difficulty will kind of come down. That's what I'm predicting will happen. So so far we don't have this should look exactly the same as what we've seen in the past, because we actually haven't crossed a difficulty period yet. So here's block 3, so we're like 3/5 of the way through, because height equals 2 means the third block. And so here we go. So here we finally we cross one of these difficulty periods. So we get to someone extends a chain to height 4, right? So height 4 would be like here, right? And then so, because there are 5 blocks in difficulty period at the moment, so the height 4 would be the 5th one. And so now we're about to cross into this next period. And so with this next period, it logs like, hey, okay, we just crossed into period 1, so this is where we're at now. Our target is 5. The duration for this first difficulty period was 22,000 or so, and we went from, so that's really high, so we decremented the bits. And so here's the question: why is this number so high? It only took like 20 seconds, 30 seconds. Why is it 2,000 for the duration? Well, the answer is because we have a hard-coded Genesis block. Remember, my Genesis block here has this hard-coded timestamp. And so 2,000 is the number of seconds it took me from the time I wrote that to the time I got to this point in the video. So you can see I've been sort of like, redoing stuff, and, I never record these things smoothly. And so another thing you'll notice is that, so these logging statements all happen twice. So they happen once when we assemble the block at height equals 5, but it also happens when we mine the block at height equals 5, and then when we are actually validating it, we will be logging once again the same exact statement. So one small change we should make as like a final change is make it so, like, let's say we only log this when we validate the block, not when we construct it. And I'll show you how to do that, just to make sure that we don't do any like redundant logging, just because it sort of pollutes the logs. And so here, once we get to the second difficulty period, we can say period equals 2, target equals 5, duration now is at 12 seconds. So that's getting closer. It's still not down to 5, but and because of that, we're going to decrement the bits from 16 to 15. Once again, redundant logging. And so here, oh, this is interesting. So all 3 blocks, oh, that's hilarious. So all 3 blocks mined the 14th, the height 14 at this independently, right? So this must have been remember our disrupt function that simulates latency and packet loss. That had a hell of a time here and really messed things up. So everyone mined their own independent blocks. But you can see that eventually, so we had a reorg, we had a couple reorgs, but eventually they all sort of agreed, and this is like the last guy to do it, so we'll just read his log. Well, you can see, because everybody did see how the durations are all slightly different, right? They're all slightly different. Let's see. Yep, this one's different too. right? The durations were all slightly different, so you can see in that they all mined independently. But eventually, this guy's block won, and so the guy, so the guy who mined first, he was able to find the next one first, and so you see he won because eventually everybody, the two that didn't agree said like, yeah, I will accept that now, and so so this guy won, it looks like, and so we went from 15 to 14 bits because we haven't gotten down to 5 seconds yet. And this is the third period, and so let's keep going. And so here we finally get to duration is equal to less than 3. And this is the fourth period. And so you can see that now that it's below 5, right? Because 5 was our blocks per difficulty period. Or excuse me, 5 was our difficulty period in seconds. And that's because we have, this is 1 times 5. So this would also be 5. So so just a little review why I'm saying these numbers, and so you can see now we've gone too far. Our problem is now too easy, so let's make it harder, right? And so if you just watch this run for a while, it'll sort of like hop back and forth. So it's getting up to 16 down to 13. So it's not exact, but you'll notice it sort of like always sticks around in this range, and so it's a safe assumption that it'll spend just as much time above the target of like the perfect numbers below it. And so it's a pretty nice little system we have, isn't it? And so let's hop back over here and remember where I was saying that there was some like redundant logging, right? It would log once and then it would log again. So let's eliminate that. And it's just going to be a simple change. So in this get next bits, we're just going to pass a log flag. So by default, it will be false. And so we're going to just hide the logger behind the log flag. And then so let's say that invalidate block when we actually check that the bits are correct here, right? So let's say here we say, we'll say log equals true here. And so then in the other place we use it when we construct the block, log will be false by default and it won't log. So if we hop back over here and run it again, we'll see that we only log once per difficulty period, and now our code is really working nicely, I hope. So they're taking their sweet time getting set up here. And I guess I got the difficulty bit set kind of high, so they're mining slow. So we got 2 here. They're almost to the end of the first difficulty period. And so remember last time when they mined a block at height 4, it did print out the difficulty adjustment stuff, right? So this time it doesn't, right? It didn't print out. So it waits till it verifies this block, the next block, until it waits till it verifies the block at height 5 and to log, and it doesn't log when it constructs the block at height 5, right? Because as soon as we mine the block at height 4, we will be constructing the block at height 5. And so now, when we are actually going to verify the block at height 5, then we get the logging. And so you see that we had a bunch of reorgs, so we had a couple, two guys logged it later, but they're all logging this is only because a reorg happened. And so if we follow it down, and this one also has reorgs, so here's one where we only everyone only logs it once. And here's a little better one. Everyone only logs this guy once. So our logging is a little bit better, and you can see the difficulty adjustment at work just by inspecting the logs. And I gotta say, this is pretty amazing. I will argue that this is basically Bitcoin. It doesn't have a lot of the bells and whistles, like it doesn't have Merkle trees, which allow for SPV wallets. What else doesn't it have? It doesn't have addresses. It doesn't have wallets. It doesn't persist anything to the disk, like it doesn't save the .dat files. It doesn't. Its algorithms for difficulty adjustment and a couple other things aren't exactly the same thing as Bitcoin, but I gotta say it's pretty damn close. Like it is. I think in all the like the heart and soul of it has all the core mechanics are here, and I think that's pretty amazing. That in let's see how many lines of code we had. So in 722 lines of code, we managed to basically replicate Bitcoin. And of course, there's bugs here. There's attack vectors. I'm sure there are problems hiding in this code. But the beautiful thing is like in the coming weeks, if you're a paid student at BUIDL Bootcamp, we're going to launch this network, and I think that's when the real fun begins. We're going to see all of the ramifications of running one of these in production. It's like all the fun of a shitcoin, but none of the like moral compromise, and so we're going to deploy this thing, and we're going to go and see all the problems it has, and so I think that's going to be even more fun than building it in the first place. And so yeah, I mean, this just kind of pat yourself on the back. I mean, if you made it all the way through these videos, I think you really have a pretty deep understanding of Bitcoin. And let's hop back over the slides and just sort of like review what we've done. So if you recall, we started with PNG Coin, right? It was the worst digital cash I could think of, and none of you have come up with a better or a worse idea. So I think I still have the record there. And so with ECDSA Coin, we eliminated counterfeiting and forged transactions by replacing photographs of analog signatures with digital signatures, right? Using the unique properties of software to do something kind of magical. Next, we created Bankcoin. Bankcoin eliminated double spends, and it did that by basically centralizing validation. You weren't responsible for validating coins yourself. You outsourced that job to the bank. Then we made Bank Diviscoin. We made transaction construction more flexible and allowed for multiple inputs, multiple outputs, and we could make if you have a bunch of coins, you could just send a very small amount of them to someone else. And so the next thing we did was we made this Bank UTXO coin where we would cache the unspent outputs and made it so we didn't have to do a for loop over the entire blockchain every time we tried to validate or construct a transaction. Next was BankNet Coin, where we added the first sort of hack at an internet protocol, in which we kind of extended as the class went on. Then came Blockcoin. Blockcoin reduced centralization by moving from one bank to many banks. It was basically EOS. Next comes POW Coin, where we did peer-to-peer networking, mining, initial block download, protocol handshake, right? And these were all like very heavily intertwined. And Nakamoto consensus reorg, so we could have actual branches and competing chains. And lastly, we came to Bitcoin, and we implemented halvenings as a solution to the global inflation problem and difficulty adjustment. This should really say halvenings plus fees, but I mean, let's just give me a break. And then difficulty adjustment as a solution to the local inflation problem. And so, yeah, I mean, that's pretty much it. I mean, the next step is to launch this sucker. So if you're, if you're in BUIDL Bootcamp, you're going to have a lot of fun launching this thing and learning. We're going to build like an exchange where we use Lightning Network to trade this token. It'll probably only be worth a few sats, but at the end, I'm going to we're going to raffle off some maybe a Casa node or a Trezor, something like that. And so these tokens should have a little bit of monetary value because they do represent rights in an auction or like a raffle for something that's really cool. So a couple kind of cool things that you guys will want. And so it'll be kind of cool to see them monetize a little bit for a short period of time. And I think we'll have a lot of fun with it. So, we'll be able to build an exchange. We'll be able to build a block explorer. We'll be able to graph how difficulty changed over time. One of the really cool things you could do is, let's say, in running this mine block, let's say if you had a CPU with 4 cores, what if you could run a different miner on every core, right? So now in Python, you can only use 1 core of your machine. if you had one of these running on every cores of your machine, you'd get 4 times the hash power. Well, I'm sure with a little bit of changes, you could make this run on a GPU. That would be pretty cool, wouldn't it? Run this on a GPU. You could have probably 10 times more hashes than you could on a CPU. And even on the CPU, if you got this work on multi-cores, you could spin up, just for the hell of it, for like an hour, you could spin up like an AWS instance with like, thousands of CPUs. And so what you could do is you could point that at the network and mine for like an hour. And so these CPUs cost like, usually like $1 per minute, or is it $1, maybe $1 per hour? I think $1 per hour. So it only costs $1 to mine for an hour on this network, and you'd probably like just absolutely destroy it. So I think that would be a lot of fun. And like, you could even go so far as like if one of you has an ASIC, like an actual Bitcoin ASIC miner, like if you've modified the firmware to that miner, so you'd actually pass in, if you could make it so you could actually pass in like these Python serializations of objects, like you could probably hack one of these miners and actually have an ASIC mine this network. Like that would be super, super fun project. So that's just a few ideas. I mean, there are tons more. I think it's going to be a blast. And yeah, so let's launch this thing. If you're not in the class, sign up, join us. It's going to be a lot of fun. There's a lot more to the bootcamp than just these videos. This is like 20% of it probably. So yeah, that's it. Thanks for learning with me, and look forward to doing more stuff together in the future. Bye bye.